So when working out stoichiometry problems involving gases, you have to remember the conversion factor to get from moles to liters of gases, and that's that there are 22.4 liters of any gas in 1 mole of any gas. Do not use that conversion for liquids or solids. Okay? It's only for gases. That ends up being a real common problem in the next unit. All right. And it's only for gases under STP, standard temperature and pressure conditions, which is 0 degrees Celsius and 1 atmosphere. Okay, but it is a real common conversion factor you'll need. So here's another example that's just a straightforward stoichiometry problem where you would use the 22.4 liter conversion factor. This is asking you how many grams of water form when you react hydrogen and oxygen gas. And by the way, this is a really cool reaction. And so the given information is that you start with 1.24 liters of hydrogen gas and wants to know how much water you make. So as always, you start with the given information, 1.24 liters of hydrogen gas. Go to moles first. So there are 22.4 liters in 1 mole of any gas. Then the mole-to-mole ratio of what you're working with, which is hydrogen, to what you're trying to get to. We're trying to get to water, which is in the gas phase in this reaction. There are 2 moles of water for every 2 moles of hydrogen, so it's really a 1-to-1 mole ratio. And then the problem asks for grams of water, so I need to go from moles. If I stopped right here, I would have moles of water. Since the problem's asking for grams of water, I need one last step that gets us from moles of water to grams of water, and that is the molar mass of water, which is 18, just because I've done it so much, or 18.02 grams of water in 1 mole of water. So I'm going to put the molar mass here, and then if I work that out, I will get grams of water formed. Okay, and this shows us that our theoretical yield of water is 0.998 grams. Theoretical yield is always the maximum amount you can make, and it's always determined from stoichiometry. Alright, so we're going to switch gears a little bit. I introduced the concept of kinetic molecular theory earlier in this unit, but it's worth going over just a bit in a bit more detail. The gas laws that you've covered and been using for calculations look at the behavior of gases on a macroscopic, like what you can actually view and measure. The kinetic molecular theory is just what it says actually. It looks at gas behavior on a molecular level. So that's why it's a theory. There's a lot of theory involved. It's not stuff we can actually see, but it's how scientists can explain the behavior of gases based on the molecular motion. So here are the main parts of the kinetic molecular theory. And again, that's often abbreviated KMT, just so if you see that and not have any idea what it is. And these typically are multiple choice questions on your exam, so it's good to be familiar with each of the parts of it. So the first part is that gases consist of atoms or molecules that are in continuous random motion. So all of these lines or vectors in all different directions are supposed to be showing random motion. And the second part is that the actual volume of the gas molecules is negligible. They're saying that gas particles themselves are so small that we can pretend that the volume they take up is 0 compared to the volume in between them. Okay? And that's simply because gas molecules are really far apart. Alright, so that's the second part. All right, attractive and repulsive forces between gas molecules are negligible. In other words, there are no intermolecular forces between gas molecules. Okay, so all of the work you do with liquids and solids trying to determine whether the intermolecular force is hydrogen bonding, dipole-dipole, London dispersion, you ignore all those. You assume there's no interaction between gas molecules, which is why they mix perfectly to make solutions. And so that's a key part of the kinetic molecular theory also. Collisions are elastic. What that means is that these particles, when they collide with either the container or each other, they don't lose their energy, or the energy of the system, energy of the gas as a whole is not lost. So they may transfer some of their kinetic energy to another gas particle, but the overall average kinetic energy of the whole system does not change. All right, and finally, the last part of it, the average kinetic energy of the molecules is directly proportional to the temperature in Kelvin, only in Kelvin. You may remember that graph I made where we had temperature on the x-axis in Kelvin and volume of a gas on the y-axis, and every single gas that was tested went to 0 volume at a set temperature, and that set temperature was 0 Kelvin, or minus 273 K. And that was where absolute temperature discovery came from. So not only did we discover absolute temperature from that experiment, we also came up with a Kelvin scale from that, because only when it's plotted versus Kelvin do we see a direct relationship between kinetic energy and temperature. All right, molecules, the last couple of concepts we're going to undergo or talk about in gases is diffusion of gases and effusion of gases. They sound the same, they're slightly different. And before we start talking about those laws and behavior, we're going to talk about something called the mean free path. So basically, gases travel in this random linear path until they collide with either the container or another gas molecule. The average distance a gas molecule can travel before it collides with something else is called the mean free path. Okay? That mean free path goes down, okay, and they use this letter U for a mean free path. Okay? That value goes down as pressure goes up. Why might that be? If you've increased pressure, let's say you decrease the volume, so you've squished all these gas particles closer together, they're obviously going to collide more frequently, and they will have a smaller mean free path. So again, before we start talking about effusion and diffusion, you need to understand the difference between kinetic energy of gases and their translational speed. That's how fast they move from left to right. That's translational speed, or up to down. Kinetic energy isn't just translational energy. It can be, but it can also be a molecule spinning or rotating. It can be a molecule or atom vibrating. All sorts of movement are kinetic energy, whereas translational is moving from one place to the other. So the kinetic energy of gases that are at the same temperature are the same. Okay, so the kinetic energy is the same at the same temperature for all gases. So if I have a mixture of gases and they're all at room temperature, let's say 25 degrees Celsius, and one of them is this huge monstrous molecule and another is an individual gas atom, and I ask you what is the difference in the kinetic energy, your answer is there is no difference if they're at the same temperature. It doesn't matter on their size. However, what is difference depending on their size or molar mass is their speed, their transitional speed or their velocity. Just like you may think of a person, you think of football players. The running backs and the quarterbacks tend to be smaller, leaner, faster moving players, and the blockers that tend to be larger don't move quite as fast typically. So same with a molecule or atom. The larger they are, the smaller their translational velocity is. So I just don't want you to get mixed up kinetic energy with velocity. They are different. Kinetic energy is the same at the same temperature. Molecular velocity depends also on the molar mass of the substance. All right, so if we are talking about the average velocity, okay, so that's the translational speed or movement of a gas, it is dependent on the molar mass. And as a matter of fact, it is inversely related to the square root of the molar mass. Okay? So as molar mass goes up, the velocity of that particle will go down. Makes sense, right? The larger particle is, the smaller the lower its speed or velocity is going to be. So now we can talk about effusion and diffusion. Okay, both of those involve translational speed or velocity. Okay, effusion is the escape through a little tiny pinhole. So that would be, let's say that you have a balloon, okay, and you poked a hole or a hole got poked in it. Then gas molecules are going to escape through that small little hole. That is effusion, okay? Or if you have a hole in your tire in your car, that's effusion also. So effusion and diffusion both follow the relationship of the root mean square speed of a gas molecule, and that is to say that it's proportional to 1 over the square root of molar mass. Okay? So the larger the molar mass, the smaller the speed. So if you were asked to compare the rate of effusion for different gases, let's say helium and nitrogen, the first thing that you want to do is look at the molar mass of the gases you're comparing. So the periodic table would tell you that the molar mass for helium is 4, and the molar mass for nitrogen gas, well, helium is monoatomic, He. Nitrogen gas, you'd have to remember, is a diatomic. So watch out, its molar mass is 28 grams per mole. Nitrogen is a larger particle of gas, therefore it would move slower. Okay? And therefore, the gas, nitrogen gas, effuses slower. So a balloon filled with nitrogen gas that had a hole in it would stay inflated longer. Helium has a lower molar mass. The gas would effuse faster because it's a smaller molecule, and the balloon would deflate faster. These are conceptual problems that you should be able to explain fast. All right, diffusion, or diffusion, which is different than effusion, follows the same relationship, and that is the rate of diffusion is inversely proportional to the square root of the molar mass of the gas molecule. So it follows the same law, but it's important to understand it's a different process. Diffusion is not through a tiny hole. It's a general spreading out of a gas through space. So diffusion would be if I stood up at the front of the room and had a little bottle of perfume and spritzed it, eventually the smell would diffuse, or the gas would diffuse its way throughout the room, so the people in the back of the room might eventually smell it, but it would take a while. That is diffusion. So the rate of that diffusion depends, again, on the molar mass of the gas components. All right, so there is a law or calculation that's very commonly used. It's called Graham's law, and that allows you to compare the rate of diffusion for two different gases. So let's say you're asked to get the relative rate of diffusion for two gases. Remember that the rates are inversely proportional to the molar mass. Okay, so if you're asked to do this ratio, just make sure that you put the molar mass of the gas that's on top on the bottom, and the molar mass for the gas that's in the denominator on the top. Don't forget the square root too. A lot of people will tend to do that. So let's do an example. A compound diffuses through a porous cylinder 3.2 times slower than helium. So we are comparing some gas to helium. So I'm going to say the rate of diffusion of helium, I'm going to start thinking through what I'm going to do, compared to the rate of diffusion of some unknown gas. And the unknown gas is slower, which means that helium is 3.2 times faster. Okay, I like to work with numbers larger than 1 instead of less than 1, so I put the faster one on top. What is the molar mass of the unknown gas? Well, let's see. What do we know about the rates? We know that the rates are inversely proportional to square root of the molar mass. Helium's on top here, so I need the molar mass of helium on the bottom. It's 4. I don't know the molar mass of the unknown gas. That is what I'm solving for. I'm going to put that there. So if I were to rewrite what I know so far, it would be 3.20, I'm going to just leave off this 1, equals square root of the molar mass of the unknown gas over the square root of 4, which is simply 2. Alright, so then I would just solve for the molar mass of the unknown gas, which I'll do on the next page. So if I rearrange this, I would get 3.2 times square root of 4, which of course is 2, equals the square root of the molar mass of the unknown gas. I'm sure you already know this, but the square root of a molar mass is the same thing as raising the molar mass to the 1/2 power. Those are just two different ways of saying the same thing. Alright, so now simplifying this, 6.4 equals square root of the molar mass of the unknown gas. How do I get rid of this square root sign? I do it by squaring both sides. That tells me that my unknown molar mass is equal to 6.4 squared. 6.4 squared is 41 grams per mole. That is the molar mass of the unknown gas. Alright, so here's another problem on diffusion that can be tricky simply because of the wording. But before you even get caught up in the words, what I would suggest you do is go ahead and set up the relationship that you know, and that is that the rate of diffusion for the two gases they're talking about is equal to inverse of the molar masses of each of them. So the molar mass of ammonium is 17.04, something like that, grams per mole, and that of hydrochloric acid is around 36.6 grams per mole. And those are the molar mass ratios. And what do you know about the relative rates of these two? Well, we know that the rate of diffusion of the ammonia is 0.00251 moles per 2.47 minutes, and we want to know what the rate of the HCl is. So I'm going to rewrite that so it doesn't look quite so sloppy. So what we have so far, I'm going to put X for what we're trying to solve. And I'm going to go ahead and take the square root of 36.6 and 17.04. Alright, so now we have as our ratios a little bit simplified. I can simplify it just a little bit further by finding out what this rate is for ammonia. So 0.00257 divided by 2.47, and that is equal to 0.00104. Oops, that's a 4. And I'm going to rewrite this on the next page. Alright, so now it looks a lot more doable. Now we just solve for X. And that is equal to okay, if you want to put it in scientific notation, X is a rate, and that is moles per minute. And I think the problem asked us for how many moles that the HCl would diffuse. So now we have to get from moles per minute to moles. Okay. It's assuming it's the same number of minutes that the ammonia diffused, which is 2.47 minutes. And get that out of the way. And so the amount of moles that will effuse, I should say, in 2.47 minutes at this rate is 0.00175 moles. All right? Let's see if that makes sense. We had ammonia, and the problem told us that 0.00251 moles of ammonia effused in a certain amount of time, and they asked us to calculate how many moles of HCl would diffuse in the same amount of time. The answer we've come up with is 0.00175 moles of HCl. So let's look and make sure these answers make sense. Which of these two do you expect to effuse faster? Well, ammonia had a molar mass of around 17 grams per mole. HCl has a molar mass of around 36.6 grams per mole, much larger. You would expect it to be smaller, therefore you would expect less of this gas to effuse, which is in fact what happened. So it looks like our answer makes sense. There are several different ways to work this problem. You don't have to work it the way I did. I suggest that you go back to the statement of the question and you try to work it through on your own in a way that you're comfortable with to get this answer. And this is the final concept in the chapter on gases. We've talked throughout this chapter about ideal gases. Ideal gases are ones that follow the kinetic molecular theory. Ideal gases are gases that do not have any intermolecular attractions to each other. And as it turns out, as you might expect, real gases are often behave non-ideal. And so obviously it's important for scientists to be able to know which gases may behave as a non-ideal gas and under which conditions. And so again, this type of thing might be a short essay question that you would have to handle or a multiple choice. So the first thing to understand about ideal behavior, ones that follow all the gas laws, is ideal gases, or gases behave most like ideal gases at high temperature and at low pressure. So I want you to understand why that is. If you understand, you won't need to memorize it. So remember that an ideal gas is one that has no intermolecular forces. Okay? So in order to have no intermolecular forces, they want to be far apart. Right? They don't want to be close and feeling each other. Under what conditions would gas particles be far apart? Well, high temperature, that causes things to expand and get farther apart, and low pressure. If there's low pressure, they can kind of go their own way and be far apart. Now, alternatively, the things that make a gas behave non-ideally would be low temperature. So if you start cooling a gas, they're going to start slowing down and coming closer together, and they're going to behave non-ideally. Same with if you exert a high pressure on a gas. Okay, you're kind of squishing them closer together, and they're going to behave non-ideally. So that's the first thing to understand, is under what conditions does a gas behave ideally and non-ideally. So what happens when you have a gas that is behaving in a non-ideal manner? Well, let's take argon for example. Argon is a wonderful ideal gas the majority of the time. It doesn't have intermolecular attractions. It doesn't tend to want to interact with any other gas. But if you start increasing the pressure even on argon gas, so look at the graph at the bottom, as you increase pressure, remember one of the assumptions of the kinetic molecular theory is that the gases themselves have zero volume. In other words, the gas particles themselves take up negligible volume compared to the volume in between the gas particles. So, but as we increase pressure, what do? We're squishing gas particles closer and closer together so that their volume becomes significant. And so the volume of argon, for example, at high pressures becomes, and that's the green line, the volume becomes higher than it is supposed to be. The volume of the particles themselves becomes significant at higher pressures. So what do we do if we have a gas that's behaving non-ideally? Well, instead of being able to use the ideal gas law as we're used to using in its very simple form, this ideal gas law is based on the fact that the volume of the gas is itself, the particles, is zero. So we have to have a correction for the volume because under non-ideal conditions, the volume of the gas is not zero, it becomes larger. And so the gas law becomes quite a bit more complicated. So this isn't something you would have to memorize. I would give you this equation, and I'm not even sure it would be on the test, but it might be. It might be an extra credit. And so I'm going to rearrange this equation for the gas law under non-ideal conditions on the next. And here we go. So we still have, if you look at the original ideal gas law, you've added a correction term for the fact that under non-ideal conditions there are intermolecular attractions between the particles, and you've also have a correction that corrects for the fact that the volume of the particle itself is no longer assumed to be zero. It does take up a significant volume. And so these correction factors are given in tables for various gases. And so it's just a matter of plugging it into the equation. It's not really hard math, but a lot of areas to make errors on, so you just have to be very careful. But the bottom line, if you use the non-ideal gas formula, you should end up calculating the pressure of the non-ideal gas as less than the pressure you would calculate using the ideal gas formula. Okay, because in actuality, this is weird, but the paths of an ideal gas are a little bit curved, and that's because they're feeling attractions to each other. Okay, so they kind of bend toward each other. Whereas you remember the ideal assumption, kinetic molecular theory, is that there are no interactions between the gas particles. So because the gases curve toward each other, that makes the pressure of a non-ideal gas less. Okay, it has less collisions with the container because it's curved a little bit. The result you should get from using the non-ideal gas formula is that the volume for the non-ideal gas should actually be greater than the volume for if you were to use the ideal gas equation. And that's, again, because if it's behaving in non-ideal manners, the volume of the gas particle itself becomes significant, cannot be neglected anymore. That is it. So the last 4 or 5 slides about non-ideal behavior, again, would probably be a bonus type question. So don't get too upset if it seems really complex for you. You can go to the back of Chapter 5 in your textbook. It'll give you some sample problems on working with the non-ideal gas equation.